Hi there, welcome to your lesson on Voronoi diagrams. Great topic, amazing application of the math skills we've been learning recently, very applicable in many aspects of real life. Let's take a look. Voronoi diagrams basically are this idea. Let's say you have a bunch of locations in space, okay, or let's say points on a map, and you want to say, I want to divide this thing into a bunch of zones so that when I draw the borders of a zone, I know everything within that zone is as close as possible to this point within that zone. Let me explain that. So here, this has been separated into all these zones. Within each zone, I know that every location in that zone, the closest point to it is this one here. So again, in this zone here, every location within that zone is closest to this point, not one of the other purple points. One more, if we look at this zone here, in this zone here, every location, if you said where's the closest purple dot, it would be this one right here. That is how Voronoi diagrams work. Maybe you're already imagining how these could be used in real life. Let's take a look. So Voronoi diagrams, let's talk about it. Okay, here is an example of kind of an application of Voronoi diagrams. Let's say there are 5 airports in a state represented by dots in the diagram. So here I can see 5 airports. There are, that might seem rare, but there are cities with that many airports. For example, London has lots of airports around it. So now the colored regions on the diagram indicate the points which are closest to a given airport. So this is a Voronoi diagram. For example, airport 5 is closest to all the points in the purple region. Airport 2 is closest to all the points in the green region. What do you think? How do you think this kind of diagram would be useful? What kind of questions could it help us answer? What do you think? All right, so let me just reiterate that again. In the blue zone, every location in the blue zone, if you said where's the closest airport, it would be this airport. In the pink zone, if you said in that zone, in those zones there, where would be the closest airport? Well, it would be airport 3. So a Voronoi diagram gives us those exact boundaries where everything within a zone is closest to that point in that zone. These were developed by somebody named Georgi Voronoi, who lived between these years. These diagrams have a large number of applications in science, technology, visual art, and so on. For example, in this airport example, if you wanted to say, hey, I live somewhere in a city, I want to know what my closest airport is. Well, you can divide the city into these zones, and then you'll know if you live within that zone where your closest airport is. All right, let's move on from there. Here is a map of the United States of America and all the capitals of each state. For example, here's California, and you can see the capital is Sacramento. It's not Los Angeles. It's not San Francisco. It is Sacramento. Often capitals in the US are cities that you may not expect. They are the government headquarters, but not necessarily the economic or cultural headquarters. So this is a map of the US. My question to you is, are the US state capitals, the capital cities, best situated to serve their state? Again, an example in California, Sacramento is here. Is that a good location to serve all of the state? In other words, is Sacramento equally close to every location in the state? Look at Texas. Austin is the capital, but it's kind of in the corner here. It's so far from other locations. Should the state capital be right in the center of a state, basically? That's my question. What do you think? Well, here's a map of the United States redrawn. And now you can see the zones are drawn as a Voronoi diagram. And this Voronoi diagram is developed to make the state boundaries change so that every location in the state is equally, no place in the state is further from I'm not saying that right. It is drawn so that within a state, the closest capital is its own capital. For example, look how California changed. You can see the old border here, but now the new border is this zone here, because now in that greenish zone there, the new California boundary under this Voronoi diagram, every Sacramento is now the closest capital to all those points. All right, or for example, here, now every location in this zone, this is the closest capital city. So you can see the borders really changed. All right, let's talk about some history of Voronoi diagrams as well. John Snow famous person in the UK, used Voronoi diagrams to show that the Broad Street cholera outbreak that killed 616 people in London between these years was due to contaminated water. All right, not air. Many people at that time believed it was contaminated air. Let's take a look at more of that history. London, September 1854. A cholera outbreak has decimated Soho, that region, killing 10% of the population and wiping out entire families in days. Current medical theories assert that the disease is spread by bad air emanating from the stinking open sewers. But one physician, John Snow, has a different theory. The cholera is spread through contaminated water, not air. And he is just about to use mathematics to prove he's right. At that time, London was the biggest city in the world, and along with the brilliance of its architecture and technological advances, showcased the Great Exhibition in 1851. It was also a filthy city. There was no sewage system, meant that waste was thrown into cesspits and open sewers that regularly contaminated drinking water supplies. So yes, the sewer water smelled, but that was not the cause of the disease. The cause was that dirty sewer water went into drinking water supplies. So doctors of the day blamed the regular outbreaks on the stench, believing the miasma of theory of disease that it spread through bad air. However, physician John Snow believed diseases such as cholera were spread by contaminated water. He alerted health authorities in 1849 of his theory, and he was largely ignored, in part because of this squeamishness about the fecal oral route of transmission that was involved. So the idea of saying that people were basically eating their waste while drinking their water, it was something people didn't want to talk about. Let's look at what he did. He basically created a Voronoi map of that part of London, and all the red dots represent the cholera outbreaks or cases, and then the little black triangles represent the location of wells. People at that time often didn't have running water in their apartments. They had to go to a local well to collect water. And you can see through this Voronoi diagram with basically zones created, with this zone in the middle here representing that every location in that zone, the closest well is this well. And you can see most of the cases are within that one zone. So he was able to zone off London by wells like that and then say, oh, look, most of the cases are there, therefore let's take a look at that well. And they did. They tested it and they figured out that that water well had bad water and that was causing the disease. So that is a very good use of Voronoi diagrams. So let's talk about Voronoi diagrams and breaking them up and say, how do we create them? That's the next part of this lesson. How do we make them? So zones of proximity. In both of these examples here, where would you draw a line to divide these into zones so that they are a proper Voronoi diagram where A, everything in the zone around A is the closest dot, and everything in the zone around B is the closest of these two. So how would you do that in this one here? Well, in this one, I hope you're thinking, if I drew a line straight down the middle, I would then have two zones. Everything in this zone, A is the closest location to everybody in this zone, and in this zone, B is the closest location for those people. So it's easy. When there's only two things, it's easy to create a Voronoi diagram. Just go straight in the middle. And more than that, this is important. If you connect the two locations, which by the way, in Voronoi diagrams, these locations are called seeds. If you connect the two seeds with a segment, the line that you're going to use to draw the Voronoi diagram is a perpendicular bisector. We learned that in a recent lesson. So if you draw a line that is perpendicular to this segment, and then you divide the segment in half with that one as well, because this perpendicular needs to be drawn at the exact halfway mark, right? So that is how you create a Voronoi diagram. You begin with your segment and you make a perpendicular bisector. Let's apply that reasoning to this as well. How would you draw the border lines between zones here so that you have a zone around A where every location in that zone, A is the closest of the three seeds, and the zone around B where every location in that zone, B is the closest seed, and so on? How would that look here? Well, it would kind of look like this in this case, okay? There's our three zones by Voronoi diagram. Okay, everything in the blue zone, everywhere in the blue zone, no matter where you stand in blue, C is your closest seed of these three seeds. And everywhere in the green zone, A is your closest seed. Okay, how do we draw those? Well, again, a reminder is you can draw segments between two seeds and then draw a perpendicular bisector. So draw a perpendicular bisector. It cuts the segment in half and it's perpendicular. And if you do that with everyone, so join those, perpendicular bisector, join these, perpendicular bisector, guess what? That is how you've made the borders of your Voronoi diagram. Again, with two or three seeds, it's pretty easy. It gets more complex when there's more seeds, but that's the general idea, and if you get that, you're able to move on here. Another key point with Voronoi diagrams is this. Now, this diagram looks a little complicated. Let me break some pieces down. Let's say we have three seeds, A, B, and C. Okay, we've joined them with segments to make a triangle. And we've done what we did in this last one. Once we have our triangle connecting, we draw the perpendicular bisector. So let's look at that here. Here is one perpendicular bisector. Here's another. Here's another. Notice that the three perpendicular bisectors meet at a point. That point has a special name. When you draw perpendicular bisectors in a triangle, that point where they meet is called a circumcenter. And it's called a circumcenter because it is the center of a circle that can now circumscribe the triangle. Notice there's a circle here, and that is the center point. So now important to note is from this point where our Voronoi borders meet, each of your seeds is equally distant because in a circle we know there's a radius, and the radius can go from the center to C, or the center to B, or the center to A. So that means our three seeds are equally distant from this point here. That's very important in the problems we're going to solve next. Okay, so how to create a Voronoi diagram. Let's recap. And I would strongly suggest you get a page of graph paper in your notebook and follow along. Let's put these 3 points on your grid page, okay? This one is at 2, 4, this one's at 7, 1, and this one is kind of between points, but roughly 5.5, 6.5 maybe, something like that. Okay, how to draw a Voronoi diagram. Number 1, make segments between two seeds, right? Connect those and find a perpendicular bisector. You can just do this with a ruler and kind of eyeball it. Of course, in class we'll look at a very precise way to do it. For now, you can eyeball it. So what would those look like? So first I'm going to connect those. Okay, now I'm going to make my perpendicular bisectors. Here's one, roughly, right there. And now for this side, there it is, perpendicular bisector. So now we need a perpendicular bisector for AB. With the AB one, let's do some math. Let's calculate the perpendicular bisector equation. Okay, let's calculate it. We know, we've been learning in this unit all the skills to do that. It has to do with midpoints, it has to do with perpendicular lines, slopes, linear equations, all the things we've learned we're going to put together now. So let's begin by finding the slope between A and B. Okay, those coordinates, by the way, are 2, 4, and 7, 1. So the slope for AB must be y value minus y value, 1 minus 4, and 7 minus 2. Our slope is negative 3/5. Great. So what does that tell you about the slope of the perpendicular that you're going to draw here? Well, the perpendicular will have to have a negative reciprocal slope. We learned that in our last lesson. So 5/3. So when we draw this perpendicular in a moment, it's going to have this slope. Now we have a slope, but we want to make an equation of that perpendicular, equation of that line. We know the slope. To make an equation, we need a point also. Do we know a point that the perpendicular would pass through? Well, it would certainly pass through the midpoint because this is going to be a perpendicular bisector. So we need to find the midpoint. And the midpoint of this line is found using midpoint formula. So find the midpoint. Okay, the midpoint is 4.5, 2.5, which is about here. So now we know when we draw our perpendicular bisector, it will pass through there. And we know the slope as well. So let's continue with the equation. To find the equation of the perpendicular bisector, now we have a slope and a point. So use those two to find an equation. Okay, this is what we've been doing all unit long. We can use point gradient form, which looks like this, right? We put our slope here, and we insert this point into here. And that can be rearranged, of course, into a linear equation with y equals something. But once we have a linear equation, we can graph it. So we found the equation. That's great. I graphed it, I connected, here we have that. That means our Voronoi diagram will look like this. Okay, there it is, our Voronoi diagram. Once we've made the perpendicular bisectors, they give us our perfect borders for the Voronoi diagram. Now, everything in this zone, A is the closest seed. Everything in this zone, C is the closest seed, and so on. All right, and just a reminder about the circle idea. Once we have that point in the middle where they meet, that point is the circumcenter, or the center of a circle that goes around. If we had that triangle, it would wrap around that triangle. And now every seed is equally distant from the center. That's very important. All right, to be continued, a couple more things to look at. Okay, let's look at a couple more. This was a Voronoi diagram with 3 seeds. Now let's look at one where we have 4 seeds. You can again draw this in your notebook, place the points at these exact locations you see here, and let's see if we can create a Voronoi diagram. Let's not worry about the algebra, the finding of the equations of the lines. Let's just kind of eyeball it. Let's connect seeds and make perpendicular bisectors, see what we come up with. So here I'm connecting the 4 seeds. Now I have a quadrilateral. Now you need to find the perpendicular bisector of each of those segments. So kind of using your ruler, do your best. Here's one perhaps. Here's another one. Here's this one. And here's this one. If you measured these with your ruler, for example, to find the exact midpoint, and then did your best to make 90-degree angles, and again measured this to find the midpoint, measured this, you'll notice that they don't all meet at one point. They will always meet at one point when it's 3 seeds, but when it's 4 or more seeds, they won't necessarily meet at one point. So in this case, we just go like that. And there we have our borders of our Voronoi diagram. They might not always meet, okay? So a little tougher, but that's what we have. So now, here's that Voronoi diagram. Just to confirm we did it okay, looks good. And we can, again, put the circles in to check that. Now, if we put a circle with center here, it will pass through 1, 2, 3 seeds. The circles will always pass through 3 seeds, because imagine now you had the triangles connecting those seeds. This is a circle that circumscribes that triangle. So now at the other point here, there'll be another circle. And that circle passes through these 3 seeds, okay? This leads to an important kind of next consideration with Voronoi diagrams. It is this. Imagine we had these 4 locations already, and let's say they represented shops in a city or something. And this company that has these shops, let's say it's the same shop at different locations, they want to find a new location, the next best location for their next shop. Well, you could say the best location is the place that's furthest from all the current shops, right? These points here are furthest from, but equally distant from all those points. So, for example, we'll come back to that in a second. This red dot represents a place that's equally distant from A, C, and D. And that could be a good location for a new shop. Or this point here is equally distant from DBC, which could represent a good location because it's equal distance from those. All right, so let's go backwards now for a moment. I'm giving you a Voronoi diagram here. And I'm wondering, where do you think the 3 seeds are? And remember, when you place the seeds, the points, the 3 points, you will think about at each point if you connected them. For example, if you put a point here and a point here and you connected them, this would be a perpendicular bisector, right? So that might help you place these seeds. Try your best. Where would the seeds go? Give me the coordinates. Well, here they are. I hope you got something close to that. For example, again, if you connected A and B here, this one ends up being a perpendicular bisector of that segment. Or if you connected B and C, this is a perpendicular bisector of that one. And finally, if you connected A and C, that's a perpendicular bisector. So that's a little tough to go backwards and find the locations, but let's try again. But before that, again, I'm putting a central point there, drawing a circle which circumscribes that triangle, and now all 3 seeds are equally distant from that point there. Remember that. Okay, try the same thing here, working backwards. Where do you think the 4 seeds would be for this 4-zone Voronoi diagram? That means you're going to place 4 seeds out here. Again, place 2 seeds and think about this being a perpendicular bisector. It'll help you. Let's see how you do. Okay, here are the 4 locations. This one might have been a little trickier for sure. This could have been a challenge for us for sure. But if you connect those, you will notice that our borders of our Voronoi are now perpendicular bisectors for each of the blue segments. All right, and we could draw one circle that passes through 3 seeds, or another circle centered here that passes through these 3 seeds. Let's keep remembering that. All right, so now the final question and the final concept for Voronoi diagrams. Let's say we have 4 seeds already in a Voronoi diagram. Where can a new seed be placed, so a 5th location, which will be furthest from the current 4 seeds? Well, of course, you could say I could place a location way out here, somewhere way out there. It's going to be far from all of them. Yes, but I'm saying somewhere within this zone, where would you locate another seed that would then be furthest from all 4? Well, based on what we've been talking about, if you look at that center point, center of this circle, all those locations, A, C, and D, are equally distant from there, and that point is the furthest one from all 3. or the second circle, that point would be furthest from all of these points. So one of those two locations is going to be the best new location for a fifth seed that is furthest from all the current seeds. So now your job is to figure out, well, which one of these is the better one? Which is the one that's further? Well, you can think of it as radii of circles. If you could figure out how long this radius is, and if you could figure out how long this radius is, and then see which one's longer, well, the longer one would then tell you that is the better location because it is further from all the pieces, all the seeds on the outside. So that's the idea we're going to apply now to one final problem. Remember this idea that when we draw these circles, those are the two furthest points, and then find which one is further by checking the length of the radii. So here's our problem. A town has 4 coffee shops, A, B, C, and D. An entrepreneur wishes to open a new shop in town, but would like it to be as far as possible from all the other 4 coffee shops. So he knows, or she, that there are 4 coffee shops, and they want to place a new coffee shop that's furthest from both of those in town. So they're not going way out here, they're going somewhere in here. We have points P and Q here. Again, those are the points that are at the corners of our Voronoi diagram. They represent the places that are furthest from all the points. But just as we said, that point here is equally far from ABD, and this point here is equally far from BCD. So now the question is, which of those 2 points is the better one? Which is the one that's further from all the points? Is it Q? Is it P? We need to find the radii of these circles. Let's try. Let's begin here. Here's a radius. Let's figure out how long it is. Do we know the coordinates of A and Q? And here's another radius. We're going to compare that radius. So we're going to compare this length and this length to see which is further from all the points. Well, we know this location here is 5, 3.5. Okay, x value 5, 3.5 here. And this location is 8, 5. So now find the length of this radius. When we're talking about the length of something, we're talking about distance formula. So apply the distance formula here. Here we go. That radius has this length. Okay, so now we know from this point, all these coffee shops in the red circle are that far from that point. Now we want to find out this length. But for this one, we don't know as much. We know this point is definitely 1/6. But we don't know the location of this one. It's kind of in between, and we don't want to just guess it. Let's find the precise location by using some algebra. So how can we find the precise location of this? We can use the idea of this line here and this line here intersecting at that point. We've talked about this in recent lessons. When 2 lines intersect and we set them equal to each other, we can find the point. So let's find the equation of this line and the equation of this line. Line 1. How do we find the equation? This is getting more and more complex here. How do we find the equation of this line? Well, we can think of it again as the perpendicular bisector of the segment between seeds A and B. So let's find this perpendicular bisector. And over here, line 2 is the perpendicular bisector of that segment connecting those 2 seeds. So equation of line 1, okay, well, we know this point is 2, 2. We know this point is 1/6. So how about finding the slope of this, and therefore knowing the slope of line 1? What is it? Okay, the slope of AB is -4/1, this slope here. Therefore, line 1 has a perpendicular slope of 1/4, negative reciprocal. Now, we can find the midpoint of this line as well, because if we know the midpoint, we can find the equation. So find the midpoint between A and B. It is this. Now we're going to use the slope and the point that we have to find the equation of line 1. We know the slope and we know this point. So here's our equation of line 1, which can be, okay, like I said, a little complex, putting a lot of skills together, but I hope we understand the process here. We found the slope, we found the perpendicular slope, midpoint, and then made an equation. Please repeat for line 2. Can you find the equation of line 2? Here is the equation of line 2 by the same process. I found the slope of first connecting AD, I found that slope, then did the negative reciprocal to get this slope, then I found the midpoint, and then I was able to create an equation. So that's the equation of line 2. Now that we have line 1 and line 2, we can set them equal to each other, because setting them equal to each other will allow us to solve for the point where they intersect, which is point Q. So here is the 2 lines set equal to each other. Solving that, I get this x value, this y value. That is the equation of point Q. So now we can find the distance of Q to A, which is the radius of the blue circle. Find distance A to Q now that we have point Q. All right, that distance is this. So that allows us to answer the initial question. We know that point Q has this distance from those coffee shops, and point P has this distance. Therefore, point Q is the best location because it is furthest from all the coffee shops. Great job, tough problem. You can do it. Let's see you in class to do some more Voronoi diagrams.